Hello, everyone, and welcome to another episode of the Data Science Decoded podcast. I am here today with Mike. Unfortunately, Nir couldn't join. Mike, how are you today?
I'm good. No complaints. We will miss you, Nir, and hopefully we'll have you in our next episode.
Yeah, so I wanted to say that this episode that we're going to do today, the paper, we tried to do it in the past and we had technical difficulties. So, from my perspective, it's the second time we're going over this paper. But it's probably one of the most important ones from a practical perspective, in my opinion. And to our listeners, the paper is the Bootstrap method. And the title is Bootstrap Methods, another look at the jackknife.
Daniel, I have a small remark. I'd like to emphasize that the previous time we tried to record an episode about this paper. I wasn't on the episode, and these technical problems were on me. I got some technical problems on Riverside, and unfortunately, Riverside was not able to resolve this problem. So it's my first time on this paper, but for Daniel, it is the second time. So take it into account. Daniel should be more familiar with this paper than me.
And the question who is more familiar with the method, but we'll see. We'll see. So it's, again, my opinion, super important. It's from 1979. So we're like in late 70s, early 80s. And it's by Efron. He's still a professor at Stanford.
He's still a professor. Is he alive? I'm sure.
Yes, he's alive. He was born in 1938.
Okay.
His parents are Russian Jewish immigrants, so Mike and I we could relate. So again, more Jewish people on the podcast, and he invented the Bootstrap method we are gonna go over today. But also he contributed a lot to other semi-computational mathematical methods.
By the way, he's a very famous mathematician, and he has many seminal papers. And what is interesting that his son is also quite famous mathematician. I don't remember his name, and unsurprisingly, his son is working in something in machine learning, I guess. And I think he has a lab. I'm not sure he's a professor, but he's a mathematician who is researching stuff in deep learning. I don't remember what. I think, but I don't remember in some stuff in computer vision.
Cool. So it's a really productive family. That's great.
Yeah, good genes.
Yeah, exactly. And so I'll read the abstract, and I'll add that the paper has many sections. Most of them are mathematical proofs or approximations. We won't go over them. We'll go over the algorithm itself and the important parts. So we start with an abstract. It says we discuss the following problem. Given a random sample x, capital X, between x1 to xn, from an unknown probability distribution f, capital F, the goal is to estimate the sampling distribution of some pre-specified random variable r of x and f. So the idea here, you have data and some probability distribution f. Calculate some function of those two. Could be anything. Could be the mean of the data, right? Or whatever. You want to do a classifier, whatever. So that's really cool. It's a really general problem. And he proposes a solution. And of course, it's based on he says, on the basis of the observed data X. And here he gives, throughout the paper, he talks and compares the Bootstrap to the jackknife theory, which is like decade prior, late 60s. It was introduced and probably used a lot, but we won't go into it. But it's more an approximation that can give you, given data, the mean and the variance. So it's really limited.
Daniel, I think we call it today something like leave one out. You are building the estimate.
Yeah, the jackknife is like leave one out, right? We'll touch upon it. That's totally correct. But again, not leave one out in the sense that we used to in machine learning when we evaluate methods, but also in estimation when we try to estimate.
Yeah.
The jackknife is like a leave one out, and then it's an approximation. It only works in specific cases. So he says a general method called the bootstrap is introduced and shown to work satisfactorily on a variety of estimation problems. So that's great. And he says the jackknife, which we talked about, is shown to be a linear approximation method for the bootstrap.
By the way, Daniel, I have some small questions. Why is it called jackknife? I can catch the connection.
The jackknife, I don't know exactly the meaning of, and I didn't go over the paper that introduced it.
Okay.
But we can talk about the name Bootstrap. Okay.
Okay.
There are some interesting things in this paper about the name.
Okay.
So that will be fun. It will be at the end, so everyone either skip to the end or stay tuned with us. So he starts the introduction. He says the Quinol Tukey jackknife, which are the two people that invented. Tukey is famous. Maybe we mentioned him in a previous episode. Also a great mathematician. So they say this method is an intriguing non-parametric method of estimating the bias and variance of a statistic of interest. So again, the jackknife. And also for testing the null hypothesis that the distribution of a statistic is centered at some specified point. Again, compares to jackknife.
By the way, Daniel, I think we need to remind our listeners about parametric and non-parametric estimation. In parametric estimation, we assume some distribution of unknown parameters, and we are trying to estimate these parameters. In non-parametric, we don't assume it, and it is exactly what Bootstrap is doing. We don't assume that that the mean is a normal distribution or the variance is somehow distributed. Okay, it is for example, you can think about k-means. It is also non-parametric if you are not doing optimization on k.
Yeah, thank you for that, Mike. So yeah, this method is non-parametric. So usually non-parametric means we do the least assumptions we can on the problem.
Yeah.
And he says this article attempts to explain the jackknife in terms of a more primitive method named the bootstraps for reasons which will become obvious. He says, in principle, bootstrap methods are more widely applicable than the jackknife and also more dependable. And now he describes what happens in each section. So I won't read it. I want to get to the bootstrap method, which is section number 2. And it says bootstrap methods because he offers 3 different ways to calculate the bootstrap. We'll soon go over them, but first, what's the bootstrap in the most basic sense? He says, we discuss first the one sample situation in which a random sample of size n is observed from a completely unspecified probability distribution, capital F. So again, we have capital F. It's the probability distribution out there. We don't know a lot about it, but it's something. And now we have n random samples out of it. And those n samples are characterized as capital X from x1 to xn. So each x is a random variable by itself out of this distribution f.
Yeah.
And then they denote small x, which is the actual instantiation of each random variable. So also x, the small x is between x1 and xn. So this is the actual data that we gathered. Okay, so we have capital X and small x, the actual data. And then he says, the problem we wish to solve is the following. Given a specified random variable r of this x and f, so again, any function of the data and the distribution, possibly depending on both x and the unknown distribution, that's what I said. And the problem is estimate the sampling distribution of r on the basis of the observed data x. Again, R could be what's the mean of the data, or what's the some kind of function you want to build out of the data. Whatever. Any questions on the data that you can take from natural language and build a mathematical function out of it, that could be R.
Yeah, so basically, instead of estimating just an unknown parameter, we are trying to estimate the distribution of this parameter, and in any sense, whatever you think, it is much stronger. We are not just estimating one number, one parameter, but we are trying to find some assessment of its distribution. For example, you can think about mean estimation, and then in addition of the mean estimation, which is one number based on the sample, you give in addition some distribution of this mean. Maybe it is skewed to the left, maybe to the right. In many cases, it can be quite important in decision making, for example.
Thank you for that, Mike. And now the actual algorithm and the steps. He says the Bootstrap method for one sample problem is extremely simple, at least in principle. He says, 1, construct the sample probability distribution f hat, putting mass 1 over n at each point between x1 and xn, meaning take the data that you got, x1 to xn, and build a probability mass. So give each observation 1 over n weight. So in a sense, this is like building a probability mass given the data.
You just assume actually in the estimation theory, you assume some population, and you have some samples from this population, and now you just assume that your population is just a sample, and you're sampling randomly from your newly defined population, which is your sample actually.
Yeah, so that's a great point, and I would like to elaborate. So usually we can think about it as 3 planes of abstraction. One is as you said, the population or the probability, a capital F. So it's out there. We don't know what it is. Then we sample from it. That's what we have. But then we say in the Bootstrap, okay, this sample, that's actually our probability that we're going to work with, or probability distribution. How we do it, we give each observation 1 over n weight. And then with this, now we can work, so that's like the third abstraction level, doing some calculation, be it estimation on it or answering various questions. So that's how I envision it in my mind.
Yeah, I think it is. There is a lot of truth in what you said. There is one interesting thing in this. You are sampling the replacement. Okay.
Yeah, we'll get to that. Yeah.
Okay.
Now we're gonna read it. So he says, okay, we constructed from our empirical data a distribution. Now it's fixed, so we call this f hat, because it's not f, the real distribution out there, it's the one we have, the empirical one. Now it says draw a random sample of size n from this f hat that we build, and this is called the Bootstrap sample. Okay, and he says, notice that we're not getting a permutation distribution, since the value of x star, which is this Bootstrap sample, are selected with replacement from the set x1 to xn. So again, from x1 to xn, we have n observations. What we do, we randomly choose n samples out of it. So each time we take one sample out and build something new. And we can have replacement, right? So we can get the same sample twice or even more. Because each time we draw out, we randomly take one from all the data we have.
By
And
the
that's
way,
what you wanted to say.
yeah. By the way, quite interesting thing. When you are sampling from your population, you are not doing it in replacement. Meaning, you have a very large population, say of people, okay, and you want to compute an average height of these people, okay, and you have a population of the whole world, say 10 billions of people, and you are trying to do it randomly, and then you're sampling. You're not doing it with replacement. You sampled one man or woman, and you don't put him back. Here it is different, and I don't have some clever mathematical explanation why here is the replacement. I have some hand waving arguments. I don't want to share them, but that still it is an interesting point, and you can just Google it or maybe ask LLM why. What is the subtlety of to this with replacement and without replacement for Bootstrap and the real sampling? It's just an interesting point for me.
Yeah, and that's right, and I agree. The question why you can sample with replacement and it works throughout the paper. I think he has some mathematics to show why it works. Part of it relates to consistency that we talked about Fisher, right? Because again, we're trying to estimate something here. So we have an estimator and it has the properties of consistency, sufficiency, and efficiency. But I wanted to say, so what we did, so now we sampled n times from our data and we built what's called the Bootstrap sample. Now on this sample, we can calculate whatever we want. We want to calculate the mean, we calculate the mean of it, right? Or we want to calculate some other statistic, we can do it. So that's the one step of the Bootstrap method. So we're not done yet. I will skip some math because there is a part here where he says the difficult part of the Bootstrap procedure is the actual calculation of the Bootstrap distribution. So what happened? We had one Bootstrap sample instantiation, right? We built those n samples once, but now he wants to do it many times to get a distribution. And he says 3 methods of calculation are possible. Method number 1, direct theoretical calculation, as in examples above. So the ones that we skip them, but the idea there is sometimes under specific assumptions, you can actually do an exact calculation. Usually it's the mean of some Gaussian distribution, so usually it's easy. This method is less interesting to us because we have computers, and that's method number 2, Monte Carlo approximation to the Bootstrap distribution, and that's what we use today practically, and I think that's the really strong part of this method. And again, we have an episode about Monte Carlo, I think even 2, so if you want to get into it, you can listen to them.
We'll put some links under the video.
Yeah, but in general, Monte Carlo is like running a lot of simulations, and each one is like a different world. and then you can do statistics on those worlds and get something out of it that is relevant to you. That's like how I view Monte Carlo. And here he says, okay, we can do the same with Bootstrap, meaning, as we said, we sampled with replacement n times and got one Bootstrap sample. So let's do it more. Let's go back to our data, sample again randomly n observations, get Bootstrap sample number 2. Let's go again. Sample. So like each sampling is like a different world. That's how I view it. Okay. And then we have, let's say, B of those times we build Bootstrap samples. Now we can take all of them and build like a histogram or whatever we want to do. So that's what he says. And the histogram of the corresponding values, also he assumes there's capital N experiments or worlds. And then he says this histogram is taken as an approximation to the actual Bootstrap distribution.
Yeah.
So now at the end, what you get is some kind of distribution that you can work with, and think about it as a histogram at the end. And then you can go and calculate the mean, variance, whatever you want, and you get the answer.
Yeah, and there's exactly the difference of estimating of the distribution of a parameter and the estimating of its value. Here we get a distribution. Okay, we can compute the mean of this distribution. We can compute variance of this distribution of our unknown parameters. We're estimating, some higher moments. We can think about confidence intervals and stuff like that. But here the main distinction is that here we arrived to the distribution. Okay, not just the value, but a distribution. So maybe you are trying to estimate your mean, and you built your Monte Carlo estimates on your bootstrapping samples, and then you just reveal that your mean is left skew, right skew. You don't have it in some simpler methods, and it is really important. And this is the main reason why bootstrapping is widely used today in machine learning and sometimes in deep learning as well.
Yeah, great point, Mike. And I wanted to add, first I'll close the window. I think there's noise. Just a second. Oh,
I did it before.
Yeah, I'll cut it out, this part. But okay. So I want to give a concrete example, okay, to our listeners, and hopefully it will help you understand the difference. So let's take Mike's example of, okay, I want to calculate, I have data of heights of people, and I don't want to calculate the average height. Okay, that's too boring. I want to calculate the height that is the top decile, meaning what's the height that 10% of the population are higher and 90% are lower. Right? And again, I cannot sample everyone, all the people that are alive. So let's say I sample 1,000 people and I get 1,000 samples of heights of, for this example, let's look at males, but the same would work for females. Now I have 1,000 observations. What I do next, I do a bootstrap sample. So I'll go and sample randomly. Okay, so each 1,000 times I'll go to one of those people. So randomly I'll get one person's height out and write it down. Go randomly and pick. That's why we can have a repetition, right? We can have the same sample, same person sample twice by random. So then I created a bootstrap sample, but it's one. one bootstrap sample of those people. And now I calculate, it's easy, it's a ranking, right? I rank them, and then I see where like the 10% are higher and 90 are lower. I write down this number. Then I go again, that will be bootstrap sample number 2. I randomly sample 1,000 people again from my sample, get a new bootstrap sample, rank it again, go to the 10%, write the number down.
Yeah.
Then I iterated many times. I get many numbers of this threshold, and now I can just calculate the average and then variance or some kind of confidence intervals. Okay, and I get a number. And it's beautiful because if I wanted to do it without the bootstrap method, okay, because it's a really difficult ranking problem of getting like the highest decile, mathematically speaking, just using approximation and math, it would be super difficult.
Yeah.
Right, so that's the beauty. Now I have computers and I can do this sampling quickly many times, and that's the power of the bootstrap method.
Yeah, and
Mike, you agree with me?
yeah, so I'm sure I agree. It is a very good example, and your example is just percentile. You can think about more complicated things. You can you want to estimate on your sample. Percentile is not very complicated. You can maybe you want to estimate several values and correlations between these values. For example, you want to estimate the correlations between anything. You have two estimations of your sample, two parameters of your sample, and you want to understand what is the correlation between two these parameters. And you can also do it with bootstrapping. For example, you are doing linear regression. Okay, you have a sample, you have an independent variable and dependent variable, which are not very good names, but we'll stick to it because it's simple.
Mm-hmm.
And you want to build some linear regression, you have coefficients in your linear regression. And you want to compute a correlation between two coefficients. These coefficients can be dependent, can be not dependent, and you can do it quite easily. Not very easily, but quite easily with the bootstrapping. And this is the beauty of this method, why it is used today everywhere, and why this paper is so powerful. But I think this paper is not getting enough credit.
Yeah, and I would even emphasize more what you're saying, and I'll give a concrete example from my experience as a data scientist doing machine learning models. So let's take a binary classifier, right? I have some data. Again, let's take an easy example. If somebody is sick or healthy, and I need to build a classifier given the data. Cool. I train a classifier, random forest, and I get, let's say, area under the curve, because it's a binary classifier, of 80%. Okay, and then I'm like, oh, cool, that's not bad. But how confident am I in this 80%? Right? So when you give one number in statistic, it's not enough. You should give maybe variance or hopefully confidence interval.
Yeah, exactly.
So I want to calculate now what's the confidence interval around this 80%. Right? How can I do it? Bootstrap method. I take my data, build many different classifiers on each bootstrap sample I took out of the data. And then I get distribution of area under the curves values, and I can calculate a confidence interval. And that's super relevant, because if the data is noisy, or again is weird or distributed weird, then you get really high confidence intervals, right? And then you can think, oh, maybe my classifier is really not good enough. Maybe I need more data or whatever. But many data scientists will say, oh, it's 80, good, I can move on. And that's actually a question I ask in interviews. if I do this kind of binary classification and I get an area under the curve, how can I check that I'm confident in it? How noisy, in a sense, the metric or the estimator I build,
Yeah,
right?
it, actually, it is a cool example. And when I was listening to you, I'm thinking about the size, the size of Bootstrap sample. Okay, so you have your sample of size n. It can be 1,000, for example. But what is the Bootstrap size? You need to choose. Is it 1,000? Is there any logic behind it? I don't remember. I did it a lot of times, and each time I need to Google it to ask LLM about it. I always forget it.
It's the same. Usually, it's the same size.
Okay.
Why? Why? I don't know. Maybe there's math behind, but yeah, the idea, if the whole sample is 1,000, the Bootstrap sample you build should be also 1,000. Maybe if you have like million of samples, you can build a smaller Bootstrap sample, and it will be good enough. But again, that's more on math and asymptotic various assumptions there.
By the way, if the Bootstrap sample size equals to the sample size, you can understand why you are sampling with replacement, because if you
Yeah.
sample without replacement, you get the same sample time after every time. So there's no logic to do it. Okay, but
No, I disagree here. Even
what-
even if you sample less, let's say,
less. No. I'm
no,
talking about not less. I'm talking about the Bootstrap sample
ah,
size equal. So if
yeah,
you
equal. Well, you can get by chance that each time you get a different one, but that's really rare.
uh, no, but okay.
There's a small
Uh,
probability that if you randomly take one out of your sample each time, you get only one each time,
okay,
but that's low probability.
okay.
But
And
you're right. Yeah, you get, because it's low probability. Mostly you sample some of them more than once.
yeah,
But
yeah. The order will be different, but the Bootstrap sample will be the same.
yeah,
And
we don't
and
care about order.
and you can think about the powerful of this Bootstrap approach like this. You are just measuring the sensitivity of your parameter estimation to different subsamples of your sample. For example, if you have some sample inside your sample which alters your estimation in some drastic way, you can see it if you are doing enough Bootstrap sample. You can see it on the distribution. Okay, you will get some maybe two peaks, for example. By the way, I don't remember the case, but in my work, I think it was, I don't remember in which company it was, but I built bootstrap ensemble and I get two modes distribution. So it was some kind of Gaussian mixtures.
Mm,
And think about it: if you just compute the
yeah,
mean of the sample, you just get some point between
yeah,
them.
in the middle, which is wrong. Yeah,
Yeah,
yeah.
which is wrong in any matter you look at it. It is just wrong, and it was about 10 years ago. And since then, I started to believe in Bootstrap. I
Oh.
knew it before, but I started to believe and use it every time when I see when I saw it. Then,
I would add a claim that could be semi-controversial. I think, in a sense, most of statistics prior to the Bootstrap method was about the problem of estimation, but it's tried to tackle it with doing approximation and doing asymptotic theory to see what happens in infinity. So trying to find all the different use cases and how approximations you can do, because they didn't have the ability to do those computations of
yeah,
Bootstrap. So
yeah,
once computers hit and you can do those uh, many Bootstrap samples, a lot of statistical work prior is not relevant. And I'll give you an example. Even he gives an example here. I'll show you just a second. Uh, it's at the end. He has remarks. He talks about interesting properties of the Bootstrap. So just a second of here remarks, and remark number. There's actually each remark is interesting. Here, the classical pivotal quantity is student's t statistic, right? So the idea was that okay, we assume a Gaussian distribution and we calculate with some formula that somebody derived. It's the t student, and perfect, and we get this. But he says, I can give you the exact, or not exact, much better one using Bootstrap.
Yeah.
So in a sense, you don't need to use the student t statistic anymore. If you have computer that can use Bootstrap, and you get a much better approximation.
Yeah.
Right? So many works of PhDs that done, I don't know what, prior to the Bootstrap is not relevant after this paper.
Yes. I tend to agree. Yeah.
Right? It doesn't mean you don't have to understand math or statistical probability. No. But you need to understand how to work, to take this math and combine it with the power of computers and simulation, and together do something much stronger.
And I'm going to even strengthen your claim about knowing math, about the essentiality of knowing math. If you need to understand, if you want to understand how Bootstrap works and all these theoretical guarantees of its work, you need to understand math. This paper, we didn't dive into it, but this paper has some heavy math inside. Yeah. So, and I think it is quite essential to understand at least some of it. Okay, and another point, and another point you mentioned beforehand, most of the work was parametric estimation. So we make some assumptions.
Mm-hmm.
Here, you don't make any assumption. Okay, you're just bootstrapping, you're just building your histogram, and based on your histogram, you do whatever you want to do with the distribution of this parameter. You can compute mean and variance and higher moments, whatever you want. Percentage, by the way. So, and this is the power of an infinite power of this method.
And we're closer to the end. I want to give a few words about the name. Okay, so I don't know if you've seen it, Mike. I'm going to read to everyone the acknowledgement. So he's grateful to a few professors, but he also says, I also wish to thank the many friends who suggested names more colorful than Bootstrap, including Swiss Army Knife, Meat Axe, Swan Dive, Jackrabbit, and my personal favorite, the Shotgun, which, to paraphrase Tukey, can blow the head of any problem if the statistician can stand the resulting mess. So we were this close to the Bootstrap being called the shotgun method.
Yeah.
And I think if he had called it the shotgun method, everyone would knew about it. Yeah. And it would make much more impact than the Bootstrap. That's my opinion.
By the way, Bootstrap, the word Bootstrap came from the book about, I don't remember his name, Munchausen, right?
Yeah. You can tell the story, Mike.
He tried to take him out from some, I don't remember the name in English, from some lake. I don't remember. But it is related to this book.
Yeah, so he was stuck. So he pulled himself out using his boots. So he pushed his boots and pushed himself out, which is again logically impossible, but it was like a satirical story, and he had many stories. The Baron Munchausen, or whatever you say it in Baron Munchausen. It's a famous German book with stories. So anyways, that's the origin of the Bootstrap. So the idea here, you use the data to get yourself what you want without like in a paradoxical way, in a sense.
Yes. And this is possible. Okay. Compared to an opposite to the real Bootstrap in this book, this is possible, and they are doing it for 45 years. This is paper
Yeah.
from 79, right? 1979.
Yeah.
So I doing it for more than 45 years since then. So it
And I
worked.
would emphasize again, probably the most useful method you should know if you're doing anything related to data, like really,
Yeah, data analysis.
because everything you calculate and you get a number, now you can get the confidence interval.
Yeah, exactly.
Super important. Again, unless you're doing deep learning and running on your whole data takes, I don't know, days. So it's hard to do Bootstrap on this. But it could be related to other ideas like various Bayesian uh, work, but maybe we'll touch upon this in the future. So again, it was a lovely episode. Mike, you have anything else to add on the Bootstrap?
No, no, actually no.
Cool. So thank you very much to the listeners. Uh, Feel free to like, and we're
And
gonna see
share.
you. Yeah, and we're gonna see you next time.
Bye bye.
Bye.